Hello, I'm Paul Beckwith. In the last video, I talked about Antarctic ice melt. I talked about the contribution to sea level rise from West Antarctic, East Antarctica, and also from Greenland. And I talked about some very worrying developments about a big, huge cavity forming in one of the main glaciers, Thwaites Glacier in West Antarctica, and also about some of the glacier melt rates and movement rates from East Antarctica. In this video, I'm going to get down to the nitty-gritty nuts and bolts of the scientific paper that came out very recently talking about how scientists have managed to measure this huge cavity, which is 4 kilometers wide by 10 kilometers long, extending up from the bedrock about 300 meters or 1,000 feet. The mass loss from this one cavity alone in Thwaites Glacier, this one huge hole, is about 14 gigatons. And if you compare that to the overall mass loss from Antarctica, which is pushing higher than 250 gigatons, it's a significant source of sea level rise just from one cavity, one feature that has just formed deep inside one glacier, a major glacier, Thwaites Glacier in West Antarctic. So let's get right to the science here. Okay, so on my Twitter feed, I sent this out here about this gigantic cavity, 2/3 the area of Manhattan, almost 1,000 feet or 300 meters tall. Okay, just to remind you of where it is, it's in this region here, draining into the Amundsen Sea, the Thwaites Glacier, and the whole large parts of West Antarctic are grounded. The bedrock is below sea level, so the ice is grounded there, and there's pinning points where the ice is resting. So as the ice melts back, the rates can vary depending on the bottom topography, etc. The slope, for example, whether it's retrograde, getting deeper as you go further inland, as it would be here, for example, in this case. Okay, it gets very deep here as you go further inland. Okay, so this is a paper that just came out, Heterogeneous Retreat and Ice Melt of Thwaites Glacier. Okay, so the glaciers flowing into the Amundsen Sea embayment, West Antarctica, they've undergone acceleration and grounding line retreat over the past few decades that may yield an irreversible mass loss. Notice the strong language here, irreversible mass loss. Okay, so the ice velocity, the ice thinning, and the grounding line retreat has been measured by a variety of techniques, including satellite and plane flown radar altimeters and ground penetrating radars from 1992 to 2017. Some sectors are retreating fast, 0.8 kilometers a year. The floating ice melting back at 200 meters a year, huge, while others are 10 times slower, 0.3 kilometers a year retreat, ice melting 10 times slower. So they're interpreting the results in terms of the buoyancy, slope-driven seawater intrusion. So we've got the cold circumpolar, we've got the circumpolar currents of ocean water, salty ocean water, and it's warm, it's down deep, and it's down deep, like it's denser than the fresh water near the surface, or less salty water near the surface. Remember that the density of seawater depends on both the amount of salt and the temperature. Warm water floats on top of cold water, but saltier water sinks below fresh water. So those two factors mean that you can get warm water below that's very salty, and it goes in between the ice and the bedrock, and it melts. And there's different preferential channels that are measured at different tidal frequencies. So the tides are very important, and that leads to, as the tides go in and out, the ice, depending on the buoyancy of the ice, depending on the pockets underneath, you can get a lot more mixing of that warm water, causing melting of the ice from below. Okay, so I'm going to look at the main points of this study, the main diagrams, and so this one here Okay, so basically I showed you the region previously where the Thwaites Glacier is. And what we have here is this is Antarctica, this is the region here, and there's a cutoff here, and this is rotated 90 degrees and displayed this way. Okay, so in this, the east side, the inland side would be up here. So we've got grounded ice on bedrock here. Here's the ocean here. This is the ice front in 2017. And so these are ice shelves in between. And what we have here is we have the retreat rates of the ice in kilometers per year. And this is in, now this is the green from 1992 to 2017 is the retreats. Okay, retreat rates from 1992 to 2011 is the green circle, and 2011 to 2017 is the red circle. So 92, okay, so these retreats, 0.6 kilometers a year per year, that was the retreat in 1992 to 2011, the average, but from 2011 to 2017, it's doubled. Okay, the 0.3 here is similar here, and over here, you can see that these melt rates, the retreat rates, this is of the grounding line. The movement of the grounding line has retreated in these two time periods. So what you can also see here is you can see the, where the grounding line is. So the change 2016 to 2017 is this guy here. So the grounding line is moving further and further inland as the ice melts and thins and starts being more buoyant. Okay, and depends also on the topography of the bottom. And what you can see here is you can see the green line, for example, is the grounding line in 2000. There's different color codes. So the 92 grounding line was this one here. Okay. So what you can see is there was some change, in smaller changes here, and now there's significant changes to 2011 and to present day, 2016, 2017. Well, there's no 2018, 2019 data. Okay, so this is the, so remember, we're in this region. If you rotate it, then you get this. Now, there's other data. So this is the change in vertical height, for example. This is thinner. This curve here is covering the central area. So if you look here, minus 1571, that would be about here. So if you take a cross-section from here and a cross-section from here, and then this is what you get, encompassing some of these regions here. So what you see is this is a change in height. This is a change in height between 2016 and 50-meter contour levels, grounding lines color-coded, retreat rates for 92 to 2011 versus 2011 to 2017 in kilometers per year. Where is it? Ugh. Okay, sorry, C. Sorry, I'm reading this one. That was the previous one. So this shows DZ in 17 millimeter increments, color-coded. And this is data just from, if you take the data on April 11th and 12th, 2016, and then compare it to the data on April 27th to 28th. Okay, so this is just a 16-day difference. Then what you can see is, and do the subtraction, then what you can see is how the elevation changes. So some regions, so basically this is a change in elevation, and what you can see is there's a lot of different structure here because the ice is deforming, and so you can get fine details, but you can actually get decent measurements over the space of a couple weeks and see how the glacier is changing. This is the height. Okay, the height above freeboard. So this is the land surfaces here. This is the ocean over here. This is the ice shelf here. and you can see how the height is changing. This is the actual measurement of the height, and this is the change in the height, dH, the differential, and this is how quickly the particular ice is moving. So anything red, so these red areas here, there's very fast movement. It's above 2.5 kilometers per year. Okay, it goes up to, you can read the contour lines, 3.6 kilometers per year movement of the ice in this particular region. As you go out here, the ice movement is faster. Now what you can do is at these different locations, these different points up here, you know, point A, B, C, D, E, F, okay? You can look at the change in each of these, and this is the ice loss. This is the DH in terms of the height. Okay, this is the height above the ice is poking above sea level, and you can convert that into the thickness of the ice. So it's just the scale changes here, but you can see the general trends are down, you know, and the measurements are here, minus 4.4 meters per year of loss here. But when you convert that into the ice thickness, it's losing 200 meters of thickness per year in this region, okay, which is huge. And you can see the scale of where the ice is being lost. So lots of it being lost here. This is 2014 compared to 2011, the difference, and 2017 compared to 2011. You can see how the the change in height, the loss of ice the loss of ice this is small h, so it's not ice thickness, it's loss of freeboard, if you like, is increasing over time. Okay, now here is the key finding. Okay, so what we have here is we have two transects through the ice, T1 to T2, T3 to T4. The grounding line is shown in here by the arrows. So what you can see is this is the top surface in 2014 is the blue line. This is the top surface of the ice, and this is the bottom surface of the ice. So there is a gap here above bedrock, right? So the ice is sitting on the bedrock. Now what happened in 2016, these measurements, you can see that the ice did not extend as high upward, and the ice actually is extending further from the bedrock. Okay, so the difference between the two red lines would be the thickness of the ice in any location. And this is where a grounding point was, right here, and another grounding point here. Okay, those are the dashed lines here. Whoops, if we go down here, those are the dashed lines here. So this transect crosses a grounding point here and here, which are shown here and here. Now T3 to T4 is where we get the big surprise. So this is in 2011, is the green curve, that's the top of the ice, and this is the bottom of the ice in 2011. Now we go to 2016, 2017 in the red line, and we get a huge loss of ice. Okay, and look at this feature appearing here. So this is about 4 kilometers. This is about 4 kilometers wide. It's about 10 kilometers long, and when it extends up from the bedrock, about 300 meters or 1,000 feet. So this is a huge gaping cavity or hole in this glacier. Okay, and that's on the T3 to T4 transect, and it's right up in this region here. Okay, this is a huge cavity. It's believed that this cavity has only formed in about the last 3 years, and the mass of the ice lost in this cavity is about 14 gigatons, which is enormous compared to the overall mass loss of ice from Antarctica. This one feature. Okay, so this is crazy, basically. So basically, you can read in about the details and so on, but basically it's believed that the tidal flows, because of course when you get mass loss of ice underneath the glacier, it's fresh water, but if you get the tide surging in and out with the warm salty water, then it's creating these huge cavities